Hello everyone. This is a video accompaniment for the paper The Transforter, a transformer model to predict delays in multimodal transportation networks, presented as a poster at IEEE Intelligent Transportation Systems Conference 2024. My name is Rohit Rajikumar, and along with my colleagues, we are scientists at TCS Research. Delays have seen an increase post-pandemic. 50% of the UK trains have been delayed from the busiest stations, and in Belgium, train delays have increased from 9.5% to 12.5%. These delays have an proven economic impact. UK have reported business costs of £1.19 billion because of delays, and Australia estimates the impact of delays to be 39.5 billion Australian dollars by 2031. Our objective with the paper is to provide a solution that can predict delays for the entire route with low absolute prediction error. The solution also needs to be agnostic to the transportation mode, and its accuracy should be evaluated on different regions. A further evaluation of the solution needs to be carried out to ascertain its impact on journey planning. Our contributions are a transformer-based model capable of predicting cascaded delays. It has been benchmarked against state-of-the-art models on multiple regions and transportation modes. The model is agnostic to the transportation modes, and we have proven its impact on multimodal journey planning. Our dataset consists of multiple modes like bus, metro, tram, and train. We have collected data for multiple trips and routes for these modes. These data come from four regions, essentially Belgium, UK, Krakow, Poland, and New South Wales, Australia. Our proposed model requires as input the arrival and departure delays of any three consecutive stops of trips that are in progress. With this, the model is capable of predicting the delays till the last stop in the trip. We propose a mode-agnostic encoder-decoder transformer. During training, the length of the input to the decoder is set as the total number of stops of the largest trip in the dataset. Each sample to the transformer is an entire trip, and the stops for which data is not present is padded with a constant value. We have used masking to prevent attention to the padded cells. This helps us to train the model for the entire trip rather than for a set number of stops. It also prevents the model from attending to future stop sequences during training. While training, the actual delays of the stops are fed to the decoder, while during inference, the predicted delays are used. The attention component in the transformer also assists in determining the influence of a past stop's delay on a future stop. We have used mean square laws to train the model for the four datasets chosen. We have compared the results of long-term prediction horizons on Transforter with other state-of-the-art models like TrainCNN, XGBoost, and CLFNet for trains in Belgium and UK. From the results, it is evident that Transforter outperforms state-of-the-art models in both Belgium and UK. In Belgium, the lowest percentage difference of 6% was recorded between Transforter and TrainCNN, whereas the highest percentage difference of 255% was recorded between Transforter and CLFNet. Similarly, in UK, the lowest percentage difference of 9% was recorded between Transforter and train, whereas the highest percentage difference of 104% was recorded between Transforter and CLFnet. Further, we have compared the performance of our model over long-term prediction horizons on multimodal journeys in Krakow, Poland and New South Wales, Australia. For Krakow, Poland, the transportation modes in our data were bus and tram. For bus, the lowest MAE was 24 seconds and the highest MAE was 50 seconds. For tram, the lowest MAE was 17 seconds and the highest MAE was 36 seconds. For New South Wales, Australia, the modes available in our data were bus, regional bus, city trains, metro, and light rail. For bus, the lowest MA recorded was 45 seconds and the highest MA recorded was 200 seconds. For regional buses, the lowest MA recorded was 18 seconds and the highest MA recorded was 77 seconds. For Sydney trains, the lowest MA was 12 seconds and the highest MA 85 seconds. For metro, the lowest MAE was 4 seconds and the highest MAE was 22 seconds. For light rail, the lowest MAE was 27 seconds and the highest MAE was 210 seconds. In summation, the mode with the lowest MAE was metro with 4 seconds and the mode with the highest MAE was light rail with 210 seconds. In order to test the effectiveness of our model in a real-world scenario, we have simulated two sets of real-time journeys. The first set is a set of journeys computed using timetables populated with predicted arrival and departure delays from our model. The second set is the same journeys computed using timetables populated with actual arrival and departure delays known ex post facto. Journeys from the predicted delay set are considered to have failed in comparison with the actual delay set if the stop sequences between the two journeys don't match, or if the travel time difference between the two journeys is greater than 5 minutes. We have then computed the journey failure rate of the Transforter against other state-of-the-art models for train in Belgium and UK. In Belgium, train performed closest to Transforter. In worst case, train outperformed Transforter by 2.5% and in best case, Transforter outperformed train by 7.5%. Transforter also outperformed CLF and XGBoost, in best case outperforming both by 13.5%. Similarly, in UK, train performed closest to Transforter. In worst case, train outperformed Transforter by 1.2% and in best case, Transforter outperformed train by 12%. In worst case, Transforter outperformed CLF by 34%. We also evaluated the failure rate on multimodal journeys in New South Wales and Krakow. The lowest failure rate was for New South Wales with 8% and the highest failure rate was also for New South Wales at 18%. In conclusion, we have proposed a novel model, the Transporter. It requires fewer features and is agnostic to the transportation mode. It has high accuracy for long prediction horizons, and we have proven its impact on real-time journey planning. As future work, we would like to benchmark additional modes and test the real-time performance of the model in a production environment. Thank you, and please contact us at the email ID shown on the screen for any further queries or clarifications.